Hey guys, I hope you all are doing good. In this lecture, this is the first lecture for the data structure series. In this one, we are going to start with understanding the life cycle of a C program, right? Even though this is not part of the course, this is very important to understand to basically have a knowledge of how the C code works, right? And what's happening behind the scenes. I'm not going to go into like too much detail into this stuff, but it's still, I think, important to understand it, right? Um, I'm just gonna spend like maybe the first one or two lectures in understanding pointers, memory layout, stack, etc., so that in the future we don't really have problem with this stuff, right? Okay. So the first topic is the life cycle of a C program, right? Now, um, so I've given this code on this side, right? This is the main.c. It's a very simple code. If you're not somebody familiar with C program, it's kind of like what this is doing is it's printing this pi over here, meaning 3.14. So when you run this code, it's basically going to print 3.14. This is what this means is like I'm defining a variable called 3.14 and I'm including this header file. Really don't have to go into much detail into this one, but let's try to understand what are the steps that happen, right? So there are four different steps that happen when you start a C program. So whenever you run this code, right? So whenever you run, so there's like this command, right? gcc main.c. So there can be multiple ways to run the C code, but this is the kind of the main one, how you run it. So whenever you like enter this, right? So let's say you have this main.c in your code in a file, and when you try to run this or you write this sentence in the terminal and run it, gcc main.c, there are four things that's going to happen. So first thing is pre-processing will take place. So what this will do is it will basically include all the lines with the hashtag replaces macros and includes the header files, right? I'll try to explain it in very simple words. So the preprocessor has one very important role to do. It's going to look for all these hashtags in the code, right? So the preprocessor is kind of like a certain, I should say like a software kind of a thing. It looks for all these lines with the hashtag. So it's going to look for this one and it's going to look for this one, right? What it's going to do is it's going to see that we have defined a variable pi 3.14. It's going to replace wherever this pi occurs with the 3.14. So preprocessor will replace this pi with 3.14. Basically, so we defined it so that we don't have to write the value 3.14 again. And preprocessor, what it did is it saw that we have defined that variable and it replaced wherever we used it with the actual value, right? So very simple to understand. And second thing it does is it also includes this header file. So what it's going to do is like header file is kind of like the file that contains the definitions or of what functions we are using in the code, right? So it's going to include it inside this as well. Basically, it's going to combine the two codes together and create one single file in a sense, right? Okay, so that's pretty much what the preprocessor does. In very short summary, it's going to look for the hashtags and it's going to replace them with whatever they have. So if it's an include file, it's going to replace it with that entire include file. And if it's a define kind of a thing, it's going to replace it wherever it occurs, wherever that specific variable occurs, it's going to replace it with its actual value, right? Okay. Next thing that happens is this is still, so just one thing to clear out, right? When you run this command, all of these four things are happening at one after the other. Preprocessing, compilation, assembler, and then linker, right? They all happen in this one command. And then when you run this a.out, it's going to run the actual code, right? I'll try to explain that in detail. So once preprocessing is done, once we have replaced these hashtags, etc., we're going to move on to the compilation, right? It converts the C code to assembly code, checks syntax, semantics, and outputs the object file, right? Let's try to understand what this does. So the thing is, C is a high-level language in a sense that it's easier to write, right? It's been made in such a way so that humans can write code and it is readable in a sense that even if it's in English, it's kind of like understandable by humans of what's happening, right? But the thing is that computers at the very end, they understand zeros and ones, right? The architecture of the CPUs and GPUs in such a way that they only understand zeros and ones, right? So what happens is the C code, the code that we write, needs to first get converted into assembly code. This is not the machine code. Assembly is a low-level language, which is kind of like that's what the language that was used like long time ago, right? For example, for a lot of rockets and that were sent to moon, their actual code was written in the assembly language. That's a low-level language, right? It's basically what this language is. It converts the C code into some sort of a like a low level code, which can further be converted into the zeros and ones code, right? And it is converted in such a way so that it aligns with the computer architecture. So let's say I'm using MacBook, right? My MacBook will generate a different sort of assembly code based on what the structure of my MacBook is, right? Where my CPU is, how the system actually works inside the system, right? So even if you don't understand the assembly part, just a very simple notice that the high level code is first converted into assembly code, right, in the middle, and then it's converted into zeros and ones. This compilation is actually converting the high level code, which is this code, into the assembly code, right? Maybe if you, it will be possible that you do this course learning how assembly language works, but even if not, then that's totally fine, right? Okay, so it outputs an object file. It's called this main.o. So object file, in very simple words, is just assembly code inside a file that aligns with our computer architecture, right? So maybe if it's a Windows, then that assembly file might be different, and maybe a MacBook, it would be different, right? So third thing that happens is the assembler converts the assembly code into machine code. Look, now at the very end, right, computers can still only understand zeros and ones. So even though we have this low level code, which can still be written by humans, it still needs to be converted into zeros and ones, and that's what the assembler does, right? Just in very simple words, converts the assembly code into machine code, right? Fourth thing that happens is the linker plays its role, which is combines your object file with the libraries to produce executable and links all external references. So let's try to understand what this means, right? Look, most of our code would have functions and definitions that we haven't really declared, or like we haven't defined them properly. So think about this one, right? This printf over here is actually a function, right? It's printing on the terminal, or it's going to print the actual value of pi. But where is it coming from, right? That's the important part, and that's what linker plays a role. What it's going to do is it's going to grab this definition of printf from wherever it is, and same thing if there's any other function definitions, right? We might be using, let's say, scanf, printf, etc. This is gonna, the linker is gonna go and combine it with all the uh, definitions that we have. It's basically going to grab their definitions, bring it into the code, and then combine it into a a.out file, right? So once again, combines your object file with libraries to produce executable and links external references to the code. So basically, what's going to happen is, in very short summary, it's going to look at this printf, it's going to link it with whatever library it is in. So let's say if it's defined in some library called lib.so, let's say if this is the library name, right? So it's gonna link this printf to this library so that when the code actually runs, our computer would know, okay, this printf comes from this library, so it can run what it's actually doing, right? We haven't really defined what printf does. It's still a function, so it needs to figure out what code needs to be run, and it will go to this lib.so file to find it, right? So let's try to understand one more time. Pre-processing takes care of all the hashtags. Compilation, what it's going to do is it's going to convert the high-level C code into assembly code, which is like it's like three different ways. So C code, assembly code, and then machine code. Compilation converts it into the assembly codes, checks syntax and semantics, right? Third thing, the assembler, it's going to convert the assembly code into actual machine code, which is zeros and ones. And fourth, the linker, it's going to figure out whatever function definitions we have and then link it to the libraries that we need, right? And it's going to result in a a.out file. So I hope all of this makes sense. The life cycle of a C program makes sense. The last thing is running the a.out, right? So I've given up like a very simple sentence in very short what happens, because we don't really need to go into too much detail about it. But what's going to happen is the operating system is going to load the program. So what happens is when I run the a.out, right? So when I do GCC, and then after this is done, it's going to run all these first four steps. So 1, 2, 3, and 4, right? It's going to run all these four steps, and then when I run a.out, right, that's what's going to actually run the code, right? So let's try to understand what's going to happen. First, the OS is going to load the program. So what's going to happen is that the operating system is going to actually put the program into the RAM of our system, right? I hope you understand what is RAM. And then what's going to happen is it's going to set up the memory. Meaning of setting up the memory is like, we need memory for running this code, right? There could be definitions, variables, a dynamic memory, etc. So it needs to basically create some place where it can store all the memory for this code, right? So that we have a track of what's happening in our code, and we basically have like a box or a storage for whatever we have, right? So it's going to set up the memory or the storage for our program. It's going to call a startup code. So startup code, you should kind of understand like some few prerequisites before running the code. So operating systems do this by themselves, right? But what you need to understand is like setting up everything for us, right? Like, so just some basic stuff so that things don't go wrong, in a very simple words. um, and last thing, it's going to run this code which is given over here, this main, and then it's going to clean up and exit, right? So clean up and exit, it's going to run the code, we will see the output, it's going to clean up and exit. So like, think about this, right? um, OS loads the program, like somebody comes in, sets up the program, it's being set up by the operating system into the RAM. Set up the memory, it's basically, we need storage for our entire system, right? Entire program, that's what being set up by this part. Startup code is kind of like checking all the prerequisites, making sure everything is fine. In very simple words, this is like a very simple definition of it. Runs the main, then after this, all these three steps are done, this code will be run, which will print 3.14. And once that's done, it's going to clean up and exit. So it's going to clean up all the resources it needed, whatever it used, and it's going to return it back to the computer, right? So I hope you guys understand the life cycle of a C program. I know this can be maybe a bit complicated to understand, but what you need to just understand is that there are 4 steps when you run the gcc main.c command, right, or the compilation command. And when you run a.out, these are the steps that basically happen, right? So even if you have like a general idea of from this lecture, that's totally fine. Okay, now we will move on to the part of understanding how the memory works. Okay, now let's try to understand the program execution and the memory layout, right? So far, I hope you guys understand that when you run the gcc main.c code, which is kind of like this one, right? So when you run this code, it does 4 steps, which is preprocessing, compilation, assembling, and linking, right? So that's what this step actually does. And then when you run the a.out, we can also call it a.ex. So in Macs, it's usually a.out, and in, I think, Windows, it's a.ex, right? Okay. So now let's try to understand that when you run this code, the a.out, right? When you actually run it, what happens? So first thing, what's going to happen is, just like I told you in the previous steps, memory is going to get created for this, and this is the actual layout of the entire memory, right? So these over here, I've drawn it in this way. These are high memory addresses. And these are low ones, right? Low memory address. Like, even though they're pretty big, think of this like a memory address 1, 2, 3, 4, something like going up the way, right? So these are high memory addresses. These are like low memory addresses, but they can be binary numbers or they can be hexadecimal numbers, as far as I remember, right? Okay, so this is the actual layout of how the memory is created for the program. in the lower segment, we store the code or the text part, right? Let's try to understand what does the text part means, right? It stores the compiled instructions, but it is read only. So let's say you have simple code, right? Let's say you have something like int main printf hello. So let's say I've just given like the main part. So let's say you have this printf instruction, right? So whatever the text we have, right? Whatever, for example, this main.c, this statement over here, they're all going to be stored in this code text segment, right? I hope that makes sense. Basically, like whatever it is. So our operating system is actually going to run the instructions from this code segment. That's how it will know what the flow of program is, right? It's going to go to this one and then run the code. So I hope that makes sense. It's basically the code or the text segment. It's stored in the lower part. Second thing is the data segment, right? It's very easy to understand. Stores the global slash static variables. So if you're not from a C background or if you're someone who doesn't understand what is global static variables, it's their global variables are basically variables that can be used across the entire program in any function or any place, right? For example, if I declare one at the very top of my code, that would be a global variable. Static variables, we don't really have to go into too much depth, but they're more like they retain their value, I would say. In very simple words, static variables retain their value. Global variables are like global. They are used anywhere in the entire program, right? So this data segment is for the global slash static variables. And there are two different segments in this one, right? One is the data segment, which stores the initialized globals slash statics, right? So initialized meaning that we have given a value for it. So if you look at this example, right? Int count equal 5. Let's say this is a global variable, right? So since I have initialized its value, it's going to be stored in the data segment, right? Or I should say the dot data initialized global static segment, right? And this one, BSS is where you store the uninitialized global slash statics, right? So uninitialized meaning that we have created it, we need memory for it, but we haven't really given it a value yet, right? For example, let's say you create the static int flag, right? We just declared it in our code, let's assume that. But since we haven't really declared a value yet, it's going to be stored in the uninitialized global statics part. So this will be in the BSS part, or I should say data part. Okay, so I hope the code text segment and the data segment makes sense to you guys. Let's move on to understanding what is the heap and the stack, right? So heap basically stores the dynamically allocated memory, meaning the malloc, calloc, etc. So whatever memory that we allocate during the function, right, while the function is running or the code is running, that's what you call dynamically allocated memory, right? Think about this. Let's say you are trying to store the names and the email addresses of students in your class, right? But you don't know how many students you have. Now, there are two ways you can do it. You can either initially, before the start of the program, you can create like a huge memory, right? But that would mean a lot of wastage. Let's say, even though it turns out that let's say I created a memory for 100 students, right? For my code or for their storage. But turns out that my class only had 50 students. That means I created that much memory, but then I've wasted that 50 memory, right? So what we actually do is we dynamically allocate it. So based on how many students we have, whenever a new student gets created, I can dynamically create new memory for it, right? Does that make sense? So static memory is one which is created at the start of the program, which is just like int count and a static int flag. There's already space reserved for it. We don't really need to worry about it too much, right? Dynamically allocated memory is what gets created while the execution of the code, right? Just a very simple definition. I'm not going into too much detail, and don't worry too much if you don't really understand this part, but just understand that it's more like something that gets created, memory that gets created while the code is running, right? So heap is where the dynamically allocated memory is actually stored, right? So whatever variables that I create, so this is an example of creating dynamically allocated memory in C code, right? Which is int star array equal malloc 18 into size of int. Let's try to understand the heap portion, how this works. So this declaration, right, int star arr, this will be actually stored in the stack, right? So this value over here will be somewhere inside this stack. So let's say this is here, right? It could be an address. It would be basically a memory address which points to the memory inside the heap, right? And this malloc, whatever this memory is created, right? So it's going to create 18. What this means is create 18 memory blocks size of int. So basically meaning that we need to store 18 different integers. So what it's going to do is in the heap, since a malloc, it's going to create like a 18 block int. It's going to create a block of memory of 18 integers, for 18 integers inside the heap, but that array will be stored in the stack over here. So when you need this memory, this will actually have the address to the memory inside this. So let's try to understand this, right? Array would be something like, let's say, equal 10112, right? It would basically be an address, right? Address meaning like the place where the memory is. And the heap would actually be something like this. So this would be the actual address, and at the address we would have something like this block of memory, right, which would be inside the heap. Does that make sense? I'll go into a bit more detail. I'll give a complete example of a code explaining how the entire section works. But for now, let's try to understand that this would be inside the stack segment. It would store the address, and this will be actually in the heap segment where we need the memory, right? Since it's been allocated as dynamically allocated. Okay. So finally, we have the stack. Stack stores the function call frames, local variables, and return addresses. Let's try to understand what this means, right? So the thing is, function call frames, let's try to understand each single word. Function call frames is like whatever function we create, we kind of reserve further space for it, for running that particular code. So let's say I create a function, right? Let's say I create a function, let's say int sum a int b. So let's say I created this sum function, right? All it does is it adds, it returns a plus b, or I should say x equals a plus b, and then it returns x. Let's say it's a very simple sum program, right? But what's going to happen is for every single function that we create, so we can have sum, maybe subtraction, multiplication, etc. A stacked frame is kind of like a space reserved for it inside the memory, right? So a stack frame will get created. It will be created inside the stack. Remember, the text segment, the text of this would still be in the code segment, right? But whatever memory it needs, whatever memory this function would need, whatever variables it needs, and whatever memory those variables further need, right? Those would be inside this stack over here, inside its particular own place, right? So it's kind of like all of these are different offices for different people, and then this stack further has different office or different space for each single function that we have. Remember, main is also a function, so there's also a stack frame for main as well inside this stack, right? I'm not going to, I hope that this is kind of making sense, but even if it's not really clear, don't worry too much. I'll go through like a very clear example. It will make a lot more sense, right? So function call frames, in very simple words, is kind of like space reserved for those functions for running the code inside them, right? Like space reserved for their variables, whatever they have inside it. Local variables, again, local variables which are local to the functions, right? So for example, x is a local variable, right? I created it inside this function, right? So it's going to be a local variable. Return addresses would be whatever address needs to be returned. We don't need to go into too much detail for the return addresses, but kind of think about this, right? We need to make sure that we have a good track of all the addresses inside our code, right? What is the address of the text segment? What is the address of our data? What is the address of the uninitialized global variables? So whatever the addresses we need, right? The return addresses, they're stored inside the stack as well, right? I hope that kind of makes sense. So a quick summary once again. Code text segment, this actually contains all the text, or I should say the instructions, the actual instructions. The data segment, it stores the global static variables. The data segment further has its own two sections. One is the initialized variables, which, for example, for which I have given already a value, and the uninitialized variables, which I have not declared yet. I might declare them into some value later on in my code. Right? Heap is where the dynamically allocated memory is created. How do we dynamically allocate memory? That's using malloc and calloc functions, right? So these are the functions. Whenever you see them, remember that the memory they have created is actually inside the heap. Okay. Fourth one is the stack. It stores the function call frames, local variables, and the return addresses. Meaning function call frames, meaning the space reserved for all the functions or whatever the function needs. Local variables, meaning whatever variables have been created locally, right? Like for example, let's say if I create a int a equal 5 inside my main, this would be inside the stack, right? Since it's a local variable, it would be inside the stack. And then return addresses is whatever the addresses we need in order for the proper execution of our code, right? Okay, I hope this makes sense. Now I will write down a code along with its how the memory looks like for it, and then try to execute what's going to happen throughout the code. Okay, now let's try to understand a code example. I'll try to go very slow with this one and try to explain exactly what's happening, right? So by now, I hope you understand the first two parts of the lecture, right? Meaning what happens when the GCC command is run, 4 steps happen, and then when the a.out or the a.ex command runs, memory gets created, right? So now let's try to deeply understand what's happening in the memory with this example, right? So I've given this code example. I would say you guys can pause this video and just try to take a look at this code segment, but and then we can move on, right? So I'll try to explain what this is actually doing. This main is creating a value. This function is basically adding two different values and then printing them, right? So the entire purpose of this entire code over here is just to print a value, which is like a sum of two different values, right? So it's just do a sum and then print it kind of a function. But even behind this very small function, a lot of stuff is happening behind the scenes inside the memory, right? So let's talk about what happens when you do the a.out or the a.ex. So when I run the a.out, right, meaning the executable, when I do it, what happens is it's going to run this code. So let's take a look at all the segments that gets created. So the code segment is going to contain the machine code for the main, the func, and the printf statement, right? So the machine code, meaning the zeros and ones for this code segment, is going to be in this code segment over here, right? So what happens is, if we let's say we trace this code, right? If you see this one, int g, int a, these are global variables, right? They have been declared outside any function and outside the main, so they are global variables. And just like I said, the memory for global variables is reserved inside the data segment, right? And so you can see that the data segment is further into two different parts, uninitialized and the initialized. So since I have initialized the value for g, it would be inside the initialized data part, right? So some address over here, it could be anything. And then int a, since it's uninitialized, right, it would be stored in the uninitialized part, right? So global int g equal 10, global int a equal global int a, right? This a we might need in the future, so that's why we haven't really declared it yet. I've just declared this, I haven't really used it in this code, but it's just to give you an idea of where it is being stored in the actual code, right? Okay, next thing what happens is, so I hope you guys understand that main is what's going to actually start. So what's going to happen is a stack frame for main is going to get created inside the stack. So this is what it kind of looks like, right? So this is the stack frame for main, and this is the stack frame for function. Just like I said, it's like we have given like like a separate place for each and every function that we have. So we have given the separate space for main. We have given this function a separate space as well. We basically call it a frame, so that basically we have a good track of the entire flow, what's happening inside our memory, right? Okay, so what's going to happen is, if you look at this sentence over here, this is int a equal to. So basically, I'm declaring a local variable a which has the value 2, right? So if you look at inside the main frame, this local integer a equal 2 will be created. So since it's a local variable, just like I said, stack stores the local variables, right? So in the main frame, it will store this local variable a equal to with the value 2, right? So it will create memory of an integer, and inside that particular memory space, it will store this value 2, right? Second thing is, it's going to call this function, right? So I've called func a, func, and then brackets a, right? So this is what happens now. When I call it, this is going to create another frame for this function over here. So the function frame gets created, and if we go from this place over to this place over here, right? So from this one to this place we go, and let's try to understand what's happening inside over here, right? First, I create a int y equal 5. Once again, this is a local variable which is created inside the function. So this will be stored inside this over here, right? I think I made a mistake. This should be y instead. So local int y equal 5 will be created. So memory space where we are storing the integer value 5. Second thing is, I also create this integer pointer, right? I'll go into pointers in the next video, but for now, let's try to understand that pointers store addresses. They basically point to some place, right? They basically store the addresses of some place where we need to go in the memory, right? So I create this memory, and if you look at this one, right, this is the dynamic allocation function. Malloc is a dynamic allocation function. So let's try to understand this particular one in detail of what's happening. When I declare int star p, it's a local, it's locally being created inside this function, right? So this pointer will be created inside this function frame. But when I allocate the memory for it, right? So when I allocate this memory of 4 bytes, that will be created inside the heap segment, right? So malloc 4 allocated 4 bytes, and let's say the 4 bytes have been allocated this at particular address. So this is like the address over here. So let's say the 4 bytes have been created at this particular address. What's going to happen is, this pointer is actually going to store the value 0x6000, right? So this pointer would actually have this value, and the heap would have these 4 bytes at this particular address. Does that make sense? Right? So it's kind of like this will be inside the stack, but this allocated memory will be inside the heap. How do we track it? How do we make sure that they are properly connected? This stores the address, and this is where the actual memory is, right? Okay, moving on. Now what we do is, we dereference the pointer, meaning we go to that address and then we store the value x plus y. So let's try to understand what is happening, right? A equal to, I pass it into this function, meaning 2 will be passed over here, x will be equal to 2, y is declared as 5. When I add these two values, right, 2 plus 5, that value will be stored at this memory address inside the heap, because I'm storing it at a dynamically allocated memory location, right? Then what I'm doing is, I'm printing the value, right? Meaning whatever the value is at the heap location at P, print it. I print it, and then I free the memory for this heap. Very important to understand is, heap doesn't take care of itself, right? Stack takes care of everything for us, meaning it frees the memory, it takes care of all the stuff. Heap is where we need to make sure, right? Whatever memory we create inside the heap, we need to make sure that we take it back, or we free it so that computer can use it for other purposes, right? So once we have allocated memory and used it, we need to make sure that we free the memory as well, right? Once we free it and we exit this function, this stack frame for func will be removed from the stack, right? Because we no longer need it. Whatever purposes we needed it for, that's already done. So from the stack segment, this function frame will be removed. Now, once we exit this, that means this entire line has been executed, and we come back to the return 0 line, right? Return 0 meaning return the value 0. It's kind of like a function. And when this executes, the stack frame for the main will also be removed, and the entire thing will be setup, right? So the global uninitialized variables, they will be removed. Machine code will be removed from the memory, and we already removed the memory from the heap inside when we run the free command, right? So long story short, um, int a is a local variable created inside the stack, two frames for both the functions, the function frame and the main frame, which store all the memory that we need for the particular functions. Heap is where the dynamically allocated memory is stored. Data segment is where the global and the static variables are stored based on whether they are initialized or uninitialized. And then code segment is where the actual machine code for the different functions is being stored, right? Like the actual instructions of running the code. Okay. And I think that's pretty much it. I hope you guys were able to understand it. And if you guys like my lectures, I would appreciate if you can share them with your friends. And yeah, stay tuned. I will move on to the pointers in the next lecture. And that's pretty much it for this one.